So hi, welcome to this next video in linear programming. In the previous video we were talking about the canonical forms of a linear program. So if you give me a linear program that's feasible and also a basis, then I can put that linear program in canonical form for that basis. So I thought that the notation just gets a little bit overwhelming if it's the first time you've seen it. So I thought it might be useful to take a look at an example of what we were discussing in the previous video, just to make it all a bit more concrete and tangible. So here's a linear program. Here's the example that we'll work with in this video. So here's the objective function C transpose X. So this is C transpose X here, and here's our matrix constraints. Here's the matrix X equals B. So here's A times X equals B. And here's the non-negativity constraints. So this is in standard equality form as it is. And now let's take a basis, and let's say the basis is 3, 4, 5, or in other words, the columns of A indexed by 3, 4, and 5. So the third, fourth, and fifth columns of A form a basis of the column space of A. And indeed they do. And so actually, we can see that this linear program is already in canonical form for this basis 3, 4, 5. Because there's two conditions that need to hold. Condition one is that the third, fourth, and fifth columns, the columns indexed by B, need to form the identity matrix, the 3 by 3 identity matrix, since this is a full row rank matrix where the number of rows is 3, so the rank is 3. So this is a 3 by 3 identity matrix, and that's true. Anyway, so you can see it here. The third, fourth, and fifth columns do form the 3 by 3 identity matrix. And the second condition that needs to be true is that the subvector of C indexed by B needs to be zeros. And indeed, if you look at the third, fourth, and fifth components of this vector C, they are all zeros. And so that shows you that this is in a canonical form for this basis 3, 4, 5. One thing I had mentioned in the previous video is that it's particularly easy to find the basic solution for this basis once our linear program is in canonical form for this basis. So what is the basic solution? Let's call it x bar. It's going to be 0, 0, 6, 10, 4. And the 6, 10, 4 is because this b, little b vector is also 6, 10, 4. So in general, why is that true? It's because what I'll do to form my basic solution is I'll take x bar, the x bar is just the basic solution. I'll take the non-basic subvector. I want that to be all zeros, and that's where these two zeros come in. The first and second components, the non-basic components, are zeros. And then for the basic components, the subvector of x indexed by the basic components, I want that to in fact be the exact vector little b itself, because I know that I'm going to have the identity matrix in A for those basic columns, and so then it just gives me for free the fact that I need a 6 here, a 10 here, and a 4 here to take when I take the linear combination of these three column vectors from the identity matrix. I get 6, 10, 4. So I want this subvector of x bar to be a little b vector. Right, so anyways, that's why it's easy to find the basic solution once it's in canonical form. This is always what you do. But I want to keep going with this example. We said that actually not only for a given basis can we put it in canonical form, but for any basis. You give me any basis of this linear program, then I can put it in canonical form for that basis. So what if I picked a new basis? So if I crossed out the basis B being this, and if I instead wrote, let's take the basis instead to be 1, 2, 4, let's say. So, and you can just see that the first, second, and fourth columns do in fact form a basis for the column space. So this is a valid basis, and but now it's very clear that this is not in canonical form for this basis 1, 2, 4. All you need is for one of these two conditions not to hold, but in fact neither of the two conditions hold. The first, second, and fourth columns do not form the identity matrix, and in addition, the first, second, and fourth components of this C vector are not all zeros. So both conditions fail. But as we said in the previous video, we can always put this linear program in canonical form for a given basis. So let's do that in this video. And we're going to do it as we said in the previous video. I'll write out what we wanted to achieve. It's max C transpose minus Y transpose A X plus Z naught plus Y transpose B. That's what the objective function was rewritten to be. I haven't told you what Y is yet. I mean, I did in the previous video, but just now I haven't. I'll put that at the bottom. But we replaced the system of constraints AX equals B with AB inverse A. X equals AB inverse B. This is an equivalent system of linear constraints because I multiply by an invertible matrix, and all I have to do is multiply again by this matrix is inverse, and just, to go back and forth between X equals B and this system, so they're equivalent, and still the non-negativity conditions hold, and Y is the vector given that we can't just take any Y. It has to be this. If I can write it correctly, it has to be AB inverse transpose times the subvector of C indexed by B. And if we take Y to be that vector, then this will be in canonical form for the basis B, and this is our new basis B. And I thought I'd just flesh out the details of how we go through this process for this example as a model example. Okay, so we want to make both of these conditions true. So let's first make this condition true. And we kind of do them independently from each other. So we start with this condition, and instead of working with our original matrix A, we multiply by we generate a new matrix, which comes by multiplying by this AB inverse. So we need AB inverse, and then we multiply it on the left and right, and so what the matrix AB in this case is this. It's the first, second, and fourth columns of A. So it's 1, 2, 1, 1, 1, 1, and the fourth column is 0, 1, 0. And so what I'm going to do is I'm going to multiply the left and right hand sides of AX equals B by the inverse of this matrix. And so what I get is I'm trying to figure out where I want to write this at. Let's write it here. Yeah, you can still, okay, good. 1, 2, 1, 1, 1, 0, 0, 1, 0 times the matrix A, which is 1, 1, 1, 0, 0, 2, 1, 0, 1, 0. Let me correct that. 1, 0. And minus 1, 1, 0, 0, 1. I won't write this out every time, but I'll do it once or twice. Times x equals, when I wrote this is the matrix AB. I want the matrix AB inverse, so I need to say inverse here. And now the same thing on the other side. I'm multiplying both sides by the inverse of this matrix. So 1, 2, 1, 1, 1, 0, 0, 1. Oh, somehow this became a 0. I'm sorry, I'm making a mistake here. This was 1, 1, 1 here, not a 1, 1, 0. So I need to erase this 0 and replace it with 1. Just making mistakes all over the place. All right, so that should be a 1 as well. So now everything's correct. And so the inverse of this times the vector B, which is 6, 10, 4. And now we can do this multiplication explicitly. And when you compute this, you end up with the following. You end up with a new matrix, which is 1, 0, maybe I can write a bit bigger here. It's 1, 0, 0, 0, 1, 0, 1 half, 1 half, minus 3 halves, 0, 0, 1, minus a half, half, x equals 1, 5, 3. And one thing, let me just write this out, 1, 5, 3. And one thing you can notice is that So this is what results from multiplying by the inverse of this matrix. And one thing you'll notice is that we do in fact get the first, second, and fourth columns, so the columns of this new matrix, which we called A bar in the previous video. This was oh no, you can't see this. I'm really bad at this. All right, now you can see it. And I was just writing numbers down, so I don't think you missed anything major. But here's the matrix, and what I was about to point out, really, this is what we called the matrix A bar in the previous video. This new matrix, and we called this B bar, and it's no coincidence that we get 1, 1, 0, 0, 0, 1, 0, and 0, 0, 1 on the first, second, and fourth columns. In other words, the first, second, and fourth columns form the identity matrix for this new matrix A. So A bar sub B equals the identity matrix, and this is our new matrix A. And so we satisfy the first condition. And why is that true? It's true because what we're doing in this step here is we're multiplying by the inverse of a submatrix of A. So this matrix, without the inverse part of it, appears within this matrix A, and it appears on the first, second, and fourth columns. That's where these three columns come from. It's the first, second, and fourth columns. And so it makes sense then when I take the inverse of it that for those columns of this matrix, they get inverted, because this is the inverse of those three columns that appear in indices 1, 2, and 4. And so for those columns 1, 2, and 4, I should see the identity matrix, because that's exactly what happens when you multiply by the inverse of a matrix. And then some random stuff happens for columns 3 and 5. We can't really predict what's going to go on there, but none of that matters. What matters is that we will get the identity matrix on columns 1, 2, and 4, precisely because we are multiplying by the inverse of a submatrix of this matrix. Okay. Anyway, so all this is to say that we rewrote the equations. It's an equivalent system of equations, but now for this new matrix A, we have, which we're calling A bar, I guess, we do have this first condition met, that the submatrix indexed by B is the identity matrix. So that first condition, we can check that first condition off. Now for the second condition, it was a bit more, but we can still do it without too much trouble. So let me just box some area off for us to work in, I guess. And so how do we go through this? Well, we changed the objective function. We added a 0 in a funny way. So we started with ax equals b again. So we started with this system of equations. So this will probably be the last time I'll write the matrix A out. But 1, 1, 1, 0, 0, 2, 1, 0, 1, 0, minus 1, 1, 0, 0, 1, x equals, and I'm going to leave some space because I know what I'm going to do, equals b. And, oh, well, let me explicitly write out b, of course. The original b here is 6, 10, 4. And we multiplied, we took a linear combination of the rows of A, and correspondingly we had to take a linear combination of these rows, but there's only one entry in each row. And so we did that with this vector that we called y, and it consists of components y1, y2, and y3. And I wrote it as a row like this. Y1, y2, and y3. And of course it makes sense that there's 3 components because that's how many rows there are. And when we're taking a linear combination of rows, we need to take, one component for each row. So rank many components here, and there's that many here. But we didn't decide what y was yet. I mean, in the previous video, in the abstract, we did decide what it is. It's exactly this right here. But in this explicit example, if we're pretending we don't know this quite yet, or if we're just going through it naively, I should say, we haven't computed what y is yet. So it's just any y, any linear combination right now, but we'll figure out what we want it to be. And so what we did is we subtracted this side to the other side, and so this was y transpose here. This was A, and this is x, and this is y transpose equals y transpose b. And what we did is we said y transpose b minus y transpose ax equals 0. So we just moved this side over here, and then we added this 0 in a funny way to our original objective function. I shouldn't say in a funny way, we just changed our objective function in a funny way by adding 0, and 0, it can be rewritten in this strange way. So that's what I meant by funny, I guess. So the new objective function, the new format of the objective function is 2, 3, 0, 0, 0, x plus the number 0. So we haven't changed anything. But what is 0? It's this. So plus y transpose ax, minus, this is, so minus y transpose ax plus y transpose b. And so this became 2, 3, 0, 0, 0 minus y transpose a, all times x plus y transpose b. Okay, let me move that up this time. And so this is the same objective function, but what we wanted is, well, what happened here is that we changed c by compensating by adding a constant here. But what we wanted to have happen is that we want the components of c indexed by the basis, 1, 2, and 4, we want those components to be zeros. So what we really want is we want 2, 3, 0 minus y transpose a to equal 0, 0, 0. And when I say 2, 3, 0, I don't mean any old 0, I mean this 0, the 0 that occurs at the fourth index here. I mean the 2 from here, the first, second, and fourth components are the ones we're talking about. We want those to be zeros by choosing y appropriately, such that when we subtract off y transpose a, we get 0, 0, 0. So this is the condition of having our new vector c equals 0 on the basic indices, because these are indices 1, 2, and 4. We just smushed them together. Okay, and then how do we figure out what we wanted y to be? What we did is I'm just going to rewrite everything as columns, and so we just moved this to the other side, and so we got 2, 3, 0 equals a transpose y. And okay, so I did two things. I moved the y transpose a to the right-hand side, where it was just a 0 vector before, so it became y transpose a, and then I transposed both sides. So the row became a column, and when you transpose the product, it's you flip the order, so it's a transpose y now. And a transpose y, so I'll just I'll just write it out this time. Oh, I'm sorry. Okay, that's what's going wrong here. I made a slight mistake. This up to here is correct. Down here, when I'm talking about the three entries, this first, second, and fourth entries, correspondingly, I want to be talking about the first, second, and fourth entries of this vector as well. And those entries occur when I'm considering the submatrix of A indexed by the first, second, and fourth columns. And so this is really A sub B. If you really followed the previous video, you'd already been able to have corrected that for me. And so similarly, this should be A sub B transpose here. Okay, so this is a square matrix here. We're not taking the transpose of the entire matrix A. We're just taking the transpose of the submatrix of A. Okay, and so now what is this? So we know A sub B is this matrix here. So transpose of this is 1, 2, 1, 1, 1, 1, 0, 1, 0. Times y1, y2, y3. Those are the three components, and this does work out. As you can see, the number of components is correct, and that's because this will be a 3 by 3 matrix, and that's because we took basis many rows and columns. It's square, so it was based on the number of rows. All the rows are full row, were linearly independent, so it's full row rank, and that's exactly how we chose y as well, to be the cardinality, the number of rows, which was 3. So this always works out. And so we have 230 equals this times y, and so we just solved for y, and so if I go up here, we get y1, y2, y3 equals 1, 2, 1, 1, 1, 1, 0, 1, 0 inverse times 2, 3, 0. And that, when you work it out, turns out to be, should have this written somewhere, it turns out to be 5 halves, 0, 1 half, when you work this out. And again, as we said in the previous video, this matrix here, this matrix is AB inverse transpose. And you can see that this vector is C sub B. So this is what we're talking about when we say take y to equal AB inverse transpose C sub B. And again, we argue that this matrix necessarily is invertible. This 1, 2, 1, 1, 1, 1, 0, 1, 0 is invertible because from linear algebra we know that inverse and transpose are commutative operators, and so as long as the original matrix was invertible, which it is, then it doesn't matter whether you take the inverse and then the transpose, or you do the transpose and then the inverse. You'll get to the same end result. And in this case, we took the transpose and then the inverse, but we know that we have to get to the same result as if we had taken the inverse and then transpose. So and so therefore this inverse must exist, and it does. And so when you multiply this out, you get this. And so when you take this particular linear combination of the rows of the matrix A, then that's here, right? So taking the linear combination of the rows of A, and you subtract this off of the original vector C, what you get is that, or what you want to get is that the new vector C turns out to be 0 on the basic components, and that's exactly what you do get. So when you take this linear combination of the rows of A, and you plug it in here, and then you also plug it in here as well, because now we know that y equals this, and we know that b is this, so everything's explicitly computed. And so if we rewrite the objective function here, so this is, let me see how I want to write this here. Okay, let me just tell you the answer, because you can explicitly compute this at this point. That's just a basic computation. This becomes 0, 0, minus 5 halves, 0, minus 1 half, times x, plus, then this y transpose b becomes 17, plus 17. So this is the new objective function. And when I say new, I mean new formatting. It's the same it's equivalent to the original one, because all we did was add 0. All it did was change the format. And you can see now that the first, second, so this is what we called C bar in this vector here is what we called C bar, I guess transpose, in the previous video. And you can see that the first, second, and fourth columns are all zeros. And that worked out precisely because we chose y to be 5 halves, 0, 1 half, which is equal to the inverse transpose of a sub b times c sub b. That was what we needed in order to ensure that this the subvector of C indexed by B was equal to 0, 0, 0, which is what we wrote down here. This is what we wanted. Want this, and so how do we arrange for this? We solved for y in this way, and it worked. And yeah, so let me just I guess rewrite everything out. So what we have is max 0, 0, minus 5 halves, 0, minus 1 half, x plus 17. That's the objective function. And then such that this holds. It's probably kind of silly that I'm just rewriting this, but oh well, just to have it all clean in one compact place, to be formally correct about this. So I'm just copying this matrix down. This is our new matrix, which we would have called A bar in the previous video. X equals 153, and x greater than or equal to 0. And so this system of constraints is equivalent to the original system of constraints, and this objective function is the same as the original objective function. It's all just been reformatted so that now it's in canonical form for this basis B, which is 1, 2, 4. And you can see that both conditions hold. The first, second, and fourth columns of this new matrix A, I guess which we're calling A bar, the first, second, and fourth columns form the identity matrix, and the first, second, and fourth components of this new C vector, C bar, are all zeros. And those are the two conditions that we needed. So we can also check this condition off as well. And so now this is in canonical form. And so in general, you can go through this process, and you can be a bit more quick about it. You don't actually need to solve for y in each case. We already know what y needs to be because we solved for it abstractly in the previous video. Y will always be AB inverse transpose times C sub B. And so you don't need to go through this solving of y. I mean, you still need to compute it. It's exactly this, but you don't need to find what it's constrained to be. It's worth noting that it's also unique, right? It's exactly AB inverse transpose C sub B. There's not any other linear combination of y of the rows of A that would have worked. It's exactly this one. But anyways, that's how this works. You can always put a linear program, which is feasible, into canonical form for any basis, and this is the process by which you do it. So hopefully this example was helpful. In the next video, we'll actually be working out the simplex algorithm. So that will be a new experience. But it's one final thing actually. It's good to know that when we do the simplex algorithm, it's good to know that this will be a subroutine of the simplex algorithm, in that we want things to be in canonical form so that then we can find new solutions. And I'll explain what those new solutions will be at that time in the context of that video. But we will not explicitly compute the canonical form. We will just use the properties that we know the canonical form has, namely its definition, and also the fact that we can always put something in canonical form. There's no question of whether or not I can put my linear program in canonical form. The answer is always yes, assuming that we started off with a linear program where these constraints could be satisfied. And so in the simplex algorithm, you'll find a basis, and then you'll put something in canonical form. You'll take your linear program and put it in canonical form for that basis, and then you'll find. And now it's in canonical form, then you'll find the basic solution, and then you'll find an even better solution based off of the basic solution, and then you find a new basis, and then you put it in canonical form for that basis, and over again until you end with the result you want. But the point is that at many iterations of putting it in canonical form, and so this will be a subroutine that we use. We won't explicitly go through it, we will just say put it in canonical form abstractly, and then we know that these properties will hold, namely these two, and the fact that we can do it. And anyways, that'll all be made more clear in the next video. That's it for this video, so thanks for watching.